My name is Enrique Cordoba Ledesma, and I will give you a little introduction to my research here at KTH. I recently finished my master's thesis, and now I'm working in a project related to the feasibility of the on-the-road charging solutions for electrical vehicles, focused on the infrastructural analysis. So let's get started. So which is the future of the road transportation? So the road transportation right now is focused on mainly in four issues: environmental, safety, durability, and of course economy. And the improvement and development of these different four issues will lead us to the introduction of a new concept, which is known as smart highways. And what are the smart highways? Well, the smart highways is the name given to the convergence of different technologies that allow intelligent interaction between functionalities, users, vehicles, and infrastructure. And within these functionalities, for instance, we have some examples like the autonomous vehicles or autonomous driving, where the vehicles are driven without human control, energy harvesting for energy collection, and of course, the most important for me, because it's the focus of my research, e-mobility, or the electrification of the road transportation. So nowadays, the electrification of the road transportation is based in two main solutions: the static charging, as most of you already know, and the dynamic charging, which is composed by two different alternatives: conductive charging and wireless charging. The static charging is the most mature technology, and as you know, is based on the charging of the vehicle or the battery of the vehicle in a stationary position. And the other two solutions are based on the charging while in motion. This is while the vehicles are driving along the road. So here are the pros and the cons of the different solutions, and the introduction, as you know, of the static solution is being really slow in the market because the lot of shortcomings that has been proven. So right now we're focusing in the dynamic, especially in the wireless solution, because even though it's a really expensive investment for the future, seems like it will be the better solution. So this wireless charging solution for highways, the inductive power transfer systems, is the better system due to this be more powerful and more tolerant to misalignments. And how does this work? Well, basically it consists in two devices: the onboard device installed in the bottom of the vehicle, and the off-board device embedded in the pavement and connected to the grid supply. So through a magnetic coupling, we can recharge the batteries of the vehicles while they are driving. And in the whole process of this, in the whole implementation process, which is a challenge. So the challenge is how to integrate this system in a feasible and sustainable way. And as you can see, this is just some of the factors involved in all this process, like the requirements of the users, the different stakeholders, industry, governments, etc., and the economic and environmental issues, the development and improvement of these wireless technologies, the design and the construction of the grid infrastructure, and of course the development of the road infrastructure. And I'm focused on the evaluation of the e-roads structural performance to get a little bit closer to the long-term prediction of this infrastructure. Why the long-term prediction? Because as we can see in the whole cycle of the implementation process, the design stage will be really important in this case due to the lack of experience in the construction of these kind of roads. So together with the long-term performance, together with the society, environmental and economic issues, will lead us to this sustainable and feasible integration that I was talking before. So this is the framework, the big picture of my research, and for the E-road structural design, to build an optimal solution or a good solution for implementing the future, we will characterize this structure by experimental test, material characterization and validation, and computational modeling by the input of different parameters to make different configurations and solutions to try to find the best one. We can obtain different criteria failure modes from here, that this will give us a broad estimation of the prediction of this structure. And then we can, of course, with these inputs, we can use them for decision-making tools like life cycle cost analysis or life cycle assessment, and maybe write some guidelines for future construction and maintenance. So before everything, we need to know what are the requirements to integrate these inductive power transfer solutions in the pavement. And the E-road performance is based not just in the structural stability, but also in the functionality. We have to combine these two issues. And for instance, some of the considerations we have to take into account is like how to integrate these facilities and where. How will be the geometry of the pavement? How will be the protective overlay? And which will be the materials? And all these considerations have to be taking care also at the same time of the power transfer efficiency between the vehicle and the pavement. So right now we have conducted some small-scale pilot tests of the different locations, as you can see here, of the E-road infrastructure. Like in this, the module containing these facilities, we'll call it charging unit, and we evaluate 4 different locations, like the corners, the interface with the asphalt, the area where 2 consequent charging units are merged, and we compare them with a conventional pavement to see where the critical areas. And for the future, what we are planning to do is keep doing this small-scale E-road pilot test in different stages, and do a X-ray scanning to evaluate the initiation and the propagation of the cracks on the fracture, and also material characterization to get deeper and more accurate characteristics of the materials. As I said before, the aim is to combine all this information with computational modeling. By using finite elements analysis, we can integrate this charging unit in the middle of the pavement and evaluate the different behavior of the structure. And also more in the future, we're planning to do more advanced material constitutive models. And so far, what we have seen is in this small-scale pilot test is the loss of the continuity and stress and strain concentration along the interface between this charging unit and this asphalt. So we have at least identified the critical areas that will be important to further research to get an structural optimization. So we are planning to do different sensitivity analysis to prove different configurations and try the influence of the different parts of the structure, and of course trying to put some joint materials on interlayer systems to see how this reacts with a erode structure. That's it. Thank you very much.